This week you were looking at other geomorphic events that tie with what we kind of talked about last week, which is really the movement of those plates and through plate tectonics. And so we're looking at volcanoes and tsunami, and these slides are actually going to focus on some key things for volcanoes. So one of the things that's really important when we look at a volcanic eruption is going to be what they call the 3 V's of volcanism. So it's looking at viscosity, volatiles, and volume. Viscosity is looking at basically how the magma moves or the lava moves. Volatiles look at what's composed in there, in that magma and lava. And then volume, really just the sheer amount. And so if we start with viscosity, viscosity is a measure of the fluidity of a liquid. The lower the viscosity, the more liquid-like it is. So water has a very low viscosity. We can think of some high viscosity things that would be like honey, molasses, peanut butter, jelly, things that move more slowly but are certainly still a liquid and can behave like a liquid, but it's a much slower movement. Okay, there's 3 things that we can look at that when we're specifically looking at magma and lava that are going to impact what does the magma and lava look like in terms of its viscosity. So we have temperature, silicon and oxygen, and mineral content. So temperature, the higher the temperature, the lower the viscosity. So the higher the temperature, the more liquid our magma and lava is, or the easier it is to flow. This should actually make sense to you kind of in a real world situation. If you ever have to heat something, like if you're melting peanut butter or butter for any kind of situation, right, you're taking something, raising the temperature, and it actually becomes more of a liquid. And so the higher the temperature, we lower that viscosity, and so that makes our magma move very nicely and very easily across the surface. Silicon and oxygen content is really looking at our connections molecularly between silicon and oxygen and our within our magma. So if you think back to your days of chemistry when you used to draw molecules with the bonds, if we have more silicon and oxygen, we have more bonds. The more bonds we have, the higher the viscosity becomes. So basically, it almost makes it like it's harder to shift or harder to move because there's so many connections. So the higher the silicon and oxygen content, the higher the viscosity, or the less liquidy it will be like. And then lastly, we have mineral crystals. And so here we're looking at actual minerals that are within our magma and lava. It's a weird example, but I like to think of peanut butter. Chunky peanut butter is harder to spread than regular peanut butter because you have those chunks of peanuts in it. So the higher the amount of mineral crystals, the higher the viscosity as well. And so if we have a lot of silicon and oxygen and a lot of mineral crystals, we have a higher viscosity lava, which means it's harder for it to move. Again, if we go to temperature, the higher the temperature, the lower the viscosity. So we have that inverse relationship there, while the other two are a direct correlation relationship. The other thing we have to look at within our magma and lava is the volatiles. And these can be any kind of gases, including water vapor. So some are going to be things that we wouldn't want to breathe in. Some are going to be things that we find normally in our atmosphere. And how this comes into play is really we're heating up any of these gases, and they are attempting to escape out of our magma and lava. And so tying very nicely with our viscosity is we can almost determine how explosive our eruption is going to be. If we have a lot of dissolved gases in our magma and lava, if we have a low viscosity magma, so one that's very fluid-like, it's a lot easier for these gases, once they get heated up, to escape out through the magma and into the atmosphere. So think of just boiling a pot of water. You can get it kind of really rolling, but for the most part, it's pretty gentle, especially when it starts that process. If we have a higher viscosity lava or magma, and we have a lot of dissolved gases, it's much harder for these gases to push through as they get heated up, and so we end up with a much more explosive eruption style. If you ever put sauce on a stove and forget about it or leave the temperature too high, you know that once those air bubbles get up to the surface, you can really have a mess all over your stovetop because a lot of energy had come out for that air bubble to make its way through the surface through that thicker sauce than it did the water. So these kind of go hand in hand in terms of looking at explosivity of our volcanoes. Our last V is volume. So here we're literally looking at the amount that's coming out. We have basalt floods or flood basalts, they use the terms interchangeably in research, that are peaceful eruptions that are erupting for years at a time. And we're talking about hundreds of thousands to millions of cubic feet of material that's coming out from the surface. So that's our largest amount. On the opposite hand, we can have cinder cones or scoria cones, which if you remember from reading are typically single eruptive, pretty explosive, but a lot of their material is not that magma and lava, but that other pyroclastic material. So the volcanic dust, the tephra, the different types of volcanic rocks like pumice that can come out of our volcano as well. And then certainly we range in the middle there with our other types of volcanoes. What your textbook does that's nice is it puts it together in a little chart here, and so we'll kind of look at these. So if we're looking at a low viscosity lava or magma, so very liquidy, low volatile, so we don't have a lot of those gases trying to make their way to the surface, and a large amount of volume, we tend to see that we're going to have a shield volcano. Remember from reading, those are your volcanoes that are very, very wide in comparison to their height. Okay. If now we're looking at an even larger amount of volume, but the same viscosity and volatiles, that's when we get into the floods of basalts. And remember, we're looking at hundreds of thousands of cubics of feet of material coming out there. If we go to a low to medium viscosity magma or lava, so still fairly liquidy, but has a higher amount of volatiles and has a small amount of volume, that's when we get into those scoria cones or cinder cones. Pretty explosive because we do have that higher volatile content and we have a little bit higher viscosity, but again, the volume's not very large. If we have a medium to high viscosity, so we're getting into a thicker magma or lava, a larger amount of volatiles, so medium high, and a large volume, that's when we have our stratovolcanoes or composite volcanoes. And then the last two on this list are more landforms. So if we have a very slow-moving, thick magma, low amount of volatiles, so we don't have anything really then that's pushing it or putting any explosiveness in that eruption, and a small amount of volume, we actually get lava domes. We typically see this happen where the lava or the magma makes its way up through the center part of the volcano to the vent, but then never really does anything. So it just makes this little cap on the top of our volcano. And then lastly, we can have a caldera where we have a high amount of viscosity, so a very thick magma, a high amount of volatiles, and a very large amount of volume. What's happening here is after our eruption now, we have expelled all of this magma and lava pretty explosively, but we've left a pretty big empty spot now within our landform, and so basically now there's air in there and it can't support the rest of the weight of the structure of our old volcano, and so we have a collapse in that results in a caldera.